So good afternoon, ladies and gentlemen. What an exciting day. We really had amazing presentations today. Thanks for the organizers for making this event. It's really good to be here today. So as the title suggests, we're gonna talk about both Contiki and AWS, meaning that we go from building smart sensors, connecting them, and storing and processing data on the AWS side. So let's get started. So that's a little bit about me. So my name is Jugurta Berkalem, and I am an embedded systems engineer. I am also an AWS solutions architect and developer associate. I work for Smile Open Source. We provide many services. I am in the embedded and IoT division. So our daily job is helping clients to build smart and connected devices, going from the kernel to the application layer and packaging everything using softwares and tools like Buildroot and Yocto. And the last step is connecting everything to some cloud provider. Well, having this said, let's go to the talk motivation. 2 years ago, I was with a client who were developing various sensor devices. They had so many flavors, but let's keep it to 3 for this presentation. All those sensors were running Contiki, which is an OS for Internet of Things. It had great support for Texas Instruments microcontrollers. And they were using their on-premise platform to process and store the data, as well as acting remotely on those different devices. Customers can also come and visualize their data, as well as changing the device's behaviors. Well, I should say that everything went well really in the beginning. And then they started selling more and more devices, until they have started noticing throttlings and latencies. And it was even getting worse with time. The more devices they were selling, the more latencies, the more throttlings, until we started having some data losses, services that were down, and I'm not going to talk about the bad user experience that we had at that time. Well, it's clearly that this architecture cannot be scaled easily. Okay, so let's jump right to the core of the presentation. Well, you may have came across this word, which is called the WSN. This stands for the Wireless Sensor Network. So years ago, this was merely a research field, but today it's everywhere, going from industrial monitoring to environmental and home automation. This field has one goal: trying to answer the question how to build smart and connected sensors, and focusing mostly on the software for a highly constrained environment. So we're trying to answer questions like, what kind of architecture? Is it going to be some kind of microkernel or modular kernel? What kind of scheduler? Is it cooperative? Is it preemptive? Do we need some real time? What about memory? Does it have to be static or dynamic? Should we have things like coalescing in order to reduce fragmentation, for example? What kind of communication protocol stack? Of course, it has to embed some communication protocol in order to fit in the IoT field. Do we have some resource sharing and synchronization like semaphores and mutexes? So this is what WSN aims to answer the questions for. In the recent years, several OSes have been submitted, like TinyOS, Mantis, LightOS, which looks like Unix-like system, but the most known is probably Contiki. However, Contiki stopped in 2018, as you can see in the last commit in GitHub. Hopefully, there was another community who started over the project, and there another name which is called the Contiki next generation. They really improved the project, and they brought really cool features like the IRM support. Okay, having said, okay, let's go to some overview about Contiki. So Contiki is open source, meaning that you can go and grab the sources from GitHub, customize it, port it to your architecture, of course, if it's not already supported. It has great support for various architectures and microcontrollers. It is built for low power communication. It's not an extension. It supports low power communication natively. It has an excellent documentation. And the good thing about this is that they provided a great simulator used for testing a whole WSN network. Well, while working in WSN networks, you may hear the word mode. Well, every device running inside a WSN network is called a mode. Some people also say nodes, but the most common word still modes. Of course, modes can communicate inside an intranet as well as the internet, as we're going to see later. Okay, so that was a pretty introduction, but let's go now to more technical things and start by writing our first hello world. So as you can see in this code, Contiki is based on C. So we start by importing the required headers, in this case, Contiki.h. The syslog is just used for printing information on the screen. And then we can set the log prefix and the log levels. In this case, I'm using the log level information in order to get all log levels like errors, warnings, and informations. The third step is writing the process. The process is divided in two different parts. The first one is called the PCB, which is represented by the macro process. This stores information relative to the process, as well as a debugging string. Well, it's only used for debugging purposes. And the second part is represented by the macro process thread, which is the actual implementation of the process. Well, the fourth step is declaring all the processes to start at system startup. In this case, I have one process, so I'm starting this process at startup. You may have also noticed the process begin and process end, which states the process boundaries, they are mandatory. So the content every code that you write for a given process must be enclosed between those two macros. Okay, so I'm guessing maybe we can test this. Okay. So this is the basic example that I have shown you on the presentation. I'm going to compile this. Actually, we have different ways to compile. For testing purposes, you may compile for your 8086. Okay, so now if I apply a basic file utility on the executable, I can see it's an ELF 64-bit. So I'm going to run this. Yeah, and it's printing our hello world. Fantastic. Let's go back to the presentation. Okay, so this is one task. What about two tasks? So we start by declaring the two processes and the two implementations of the two different processes. And of course, we update the list of the processes that we start at system startup. And the output of this is shown on the image on the screen. Okay, In real life, we want our process to run for an indefinite time. For this, we can use a for or a while, of course, just like C or FreeRTOS. You can use the clock seconds, which returns the system's time. You can also use the clock set seconds to set the system's time. There is another API called the clock time, which returns the number of ticks since the system boot. Maybe you can see, yeah, this is better. And we have also the clock wait, which is used to create some delays. You may have seen this macro called the clock second, and this returns the number of ticks in 1 second. So, of course, this program is just printing the temperature every 1 second, as you can see on the output. Okay. So as you can see in this example, we have used clock wait to create delays. Delays are not good. They are seldom in practice. We need a much modern way to create, to create this delay using timers. Timers are a more modern way. In Contiki, we have different timers. We have the timer and S timer, which are pretty old. Do not use them because the process needs to poll on the timer expiration. And then we have a much more modern interface called the E timer and C timer, which are purely event-driven, which means that the process is awakened upon timer expiration. Personally, I prefer using the C timer because it provides a callback, because I prefer to separate the process code from the code to execute at timer expiration. For real-time purposes, you may use the R timer, which uses a high resolution clock. Let's take an example. So first of all, you have to declare the E timer structure. And then you must configure the timer. For example, in this case, I'm firing the timer every 3 seconds. And then I'm building the payload. In this case, I'm just grabbing the temperature and I'm using the sprintf in order to format the string. And then I apply some XOR encryption. And there is an important macro, which is the process wait event until. This actually makes the process free the CPU and calls the scheduler in order to schedule another process if the timer is not expired. This is how we're not wasting CPU cycles. This is very effective. Of course, don't forget to relaunch the timer. Otherwise, your timer is going to actually expire only once and never expire another time. So the output of this is shown on the screen. There are some characters that are not well displayed because of the encryption. In practice, you can use the AES 128-bit in order to encrypt your data. Okay, so let's go to the funny part of this presentation. Okay, so everything that we did so far, we did it for a single sensor. We wrote some code that can run inside the sensor. But what about if we want to make those different sensors communicate between each other? For this, Contiki has introduced the Ripple protocol, which comes in 2 flavors, the RPL Classic and the RPL Lite, which is the default one, which is the most modern one, which is the latest one. In the Ripple protocol, we introduce another node. It is a special node called the root node. Actually, this node is used to calculate all the different paths between the nodes. It is graph theory, actually. And the whole thing is called the destination-oriented directed acyclic graph. So the root node is used as a reference to compute different paths. Of course, Contiki is not limited to one level. We can have multiple levels, and this is called multiple hops routing. For example, if sensor 6 wishes to communicate with sensor 1, then the message, for example, is routed from sensor 6 to sensor 2 and then sensor 1. Okay, so let's have an example. So in this example, on the left, I have the source code for the root node. I'm just forcing this node to be a root node. Otherwise, the Ripple protocol will not be enabled. We need a root node in order to communicate modes inside the intranet as well as the internet, as we're going to see later. And then I have to register a UDP socket for both the root mode and also the sensor modes. And then the sensor mode is going to send some messages. But how it's going to find the IP addresses? We have different APIs. For example, in this example, I'm using the NetStack routing get root IP address, which retrieves the IP address of the root node. We have different APIs also, which allows to retrieve IP addresses of other modes in the WSN network. I don't have multiple modes to run the example, but we can use the Koja simulator provided by Contiki, as you can see on the picture. For example, and the good thing about this is that it can help you to understand the best distances to keep between the modes. For example, we can see that that mode number 3 is outside, is actually too far from the network. That's why it has difficulties to send the messages. Okay, so now let's go to the internet. So how can modes from WSN network communicate with the outside world? Okay, in this case, we have to promote the root node to something called the border router mode. It's exactly like a gateway. Of course, for practical purposes, you have to use multiple root nodes in order to avoid any failure. And the root node is going to be connected to some 6-LoWPAN router. And the 6-LoWPAN router will be connected to any public router, and then everything goes to the internet. Some people love to place some middleware, maybe to change or to format the data before sending them to the internet. Okay, so how can I test this setup without actually buying a 6-LoWPAN router? Actually, we can do this because Contiki provides really nice tools. For this demo, I'm going to create a root node and embed inside it a web server. Yes, we can do this using Contiki. And I'm going to turn my computer into a 6-LoWPAN router by enabling and using a tool provided by Contiki called the TuneSlip 6. Actually, it allows 6-LoWPAN communication over USB. And then I'm going to write a middleware, which is going to come and pull the data from the web server and displace them to the end user. For this demo, I'm going to use the CC2650 Launchpad development kit developed by Texas Instruments. So how can we do this? Actually, there is a good example in Contiki. You can customize it and change few things in order to make this work. First, you have to change the return type from the server to JSON, for example, and then you just set the payload. In this case, the server returns the temperature and the vibration level. Okay, it's time for the demo. So for this, I'm going to connect my mode to my computer using USB. Okay, great. And then I'm going to use the tune slip 6 provided by Contiki. Okay, it takes some time to start. Okay, great. Now that it has started, it's actually printing the IP address of the root node. For example, now to test my settings, I can ping the root node. You see, it's responding. And now I'm going to launch the middleware, which is going to poll over the web server in order to retrieve the different data every 5 seconds. You see, it works perfectly. Okay, great. I'm going to stop this. Okay, so now let's go to the second big part, which is AWS. So AWS provides more than 200 services. Most of them are scalable. They are available all the time. Of course, AWS services are known to be secure. And of course, they are focusing a lot on data integrity. The most common services on AWS are EC2, for example, which is used for virtualization, S3, which is used for storage, RDS, which is used for SQL databases. Actually, it supports today 6 different engines like MySQL and Oracle. And then we have the DynamoDB, which is a NoSQL database. And then we have the Lambda, which is used for serverless computing platform. We just can write code which can be run on AWS. And of course, the one we're going to use today, which is the IoT core, used to manage an entire fleet of IoT devices. It can scale to millions and millions of devices. Here is a picture taken from all the options provided by IoT core. So we can see a menu used to monitor the object connectivity. Objects can connect to AWS IoT core using MQTT or HTTPS, but most of the time we use MQTT. Of course, we need to have some valid certificates. AWS will never allow an object which is not authenticated to connect to AWS. Then we have another menu used to list all the devices. You can group them by types, maybe by groups. You can launch jobs on those groups, for example, to update them. And then you have a bunch of security features. For example, the certificates used to view all the certificates of your devices, and the CA certificate used to sign the certificates of your devices. We're going to talk about that later. There is something called rules, and this is very important because it defines how the messages will be routed once they are delivered to IoT core. For example, you have your device, which is sending data to IoT core, and then the rule is used to route those messages to another AWS service, for example, a database or a Lambda. And then you have a test menu, which is used for testing purposes. You can test publishing and subscribing over MQTT. Okay, so let's carry on. Technically, a device can write on any topic on AWS. Of course, devices must have a valid certificate. They must authenticate. And then it's enough to know the endpoint of AWS to which we're going to write, and you can write whatever you want. There are few topics, though, which are really, really special. The first one is the most common one. One of these special topics is called device shadow. So device shadow is just a JSON document. You can put whatever you want inside this JSON document. We can have multiple shadows attached to a given device. And every device has a default shadow. Sometimes it is referred as a name-named shadow. So administrators or users can come and write this shadow content. Once the device connects to AWS, it will retrieve the new JSON document or the new shadow to change its status. Just pay attention, there is a practical limitation. Device shadow cannot have more than 6 nesting levels. Okay, so let's take an example. There is a customer, for example, who needs to send some Contiki-NG mode from some Contiki-NG modes, some data to AWS. The data contains the temperature and vibration level. Actually, it's the example that we did earlier, but this time we're going to connect it to AWS. The data must be stored inside the NoSQL database. And if the temperature goes over than 40 degrees, we're going to send an email. Here is one possible solution. So once again, I'm using the example that we did so far. In this case, the middleware is going to write the content of the message over MQTT to some IoT rule. And the IoT rule is going to call the DynamoDB for storage, as well as the Lambda. And the Lambda is going to compare the temperature to 40 degrees. If the temperature is over 40 degrees, it's going to call the SNS service, which is going to send some email and SMS to user. In our case, we're only going to demonstrate using email. Okay, so let's go to the demo. Okay, so probably first I'm going to show the AWS. Okay, so now here I'm on AWS platform. And this is the first rule. If I come back over the presentation, yeah, this rule over here is this one. It's the entry point to IoT core. So this rule is going to dispatch the message to both a DynamoDB for storage and the Lambda function. The DynamoDB is over here. For now, it has only 3 elements. And the Lambda function is here. It is comparing the temperature to 40 degrees. And in case we are above this threshold, we send an email. So here we can see my mail. So I don't have any message. But now I'm going to actually, okay, so Tune 6 is still running. Okay, perfect. So I'm going to launch the middleware, which is going to pull over the server and send everything to AWS. Here the temperature is beyond 40 degrees. So you can see that I have received a notification. Once again, more than 40 degrees. So we have 2 notifications, 45 degrees. I'm going to have a third notification. Great. I can access now the notifications. As you can see, I have different alerts. Every time the temperature goes beyond 40 degrees. Okay, that's awesome. Perfect. I'm going to refresh the content of the DynamoDB. Okay, so we can see more elements inside the database. The data has been stored successfully. Once again, this is no SQL database. Okay, great. So let's carry on this. So here are some tips for industrial world. Of course, when you use something like an AWS or something like Azure, you don't have to set up things manually. Always use an automated tool like CloudFormation or Terraform to set up the infrastructure. Don't use it manually. Don't do it manually. You may use something called the just-in-time provisioning. The goal of this is to create your own certificate called the certificate authority. And using the certificate authority, you can sign different certificates to be used on your devices. And then you can embed those device certificates on your devices to allow them to communicate with AWS in a secure way. Of course, always tune security settings. For example, the middleware that I used now has only access to IoT Core, but nothing more. If you have different users who wish to come to visualize, for example, the data stored on AWS, you may use Cognito to allow user registration. Never forget to add some updating capabilities to your devices. Otherwise, you will have a lot of troubles. As we have seen using Contiki, the root node is used by Ripple to route the different messages in both the intranet and the internet. Always use multiple root nodes to avoid any failover. Okay, so I guess we're coming to the conclusion. Yeah, so as I have introduced in the beginning of this presentation, it's not enough to design your system. You have to think how to process and store massive data because your system is going to grow one day. We've also seen that WSN is a really prominent and growing field. There are a lot and thousands of papers out there that you can go and read. Contiki is a really great choice because it has really an active community and a wide range support for different architectures and microcontrollers. Try to use MQTT instead of HTTP. For security reasons, you may use the AS128 functionality provided by Contiki. And the last sentence, it's really personal. I'm really advising you to try different cloud providers. For example, you might try the IoT Central on Azure and compare the different providers. And something very important, try to get yourself certified. This is important. Well, here we have further reading. The first two articles, I wrote the first two articles. The first one is about Contiki and AWS. It's starting, it's kind of, it's actually summarizing everything that I have said so far. The second one is kind of getting started using AWS. And of course, Contiki-NG has an excellent documentation. I really encourage you to go and take a look at it. Well, I think this is the end of the presentation. So if you have any questions,